Good morning all of you. Let us go for today the derivations of Navier-Stokes equations. Before that Cauchy equations we will derive it, and which is a really important subject in the fluid mechanics to understand the computational fluid dynamics. I will try my level best to teach this part of these chapters as is possible. So, for but the mathematically this chapter looks like very complex, but I will try to deliver these lectures as simple as possible, not going more detail about mathematics. That is my idea, and the basically what we are going to derive it before deriving Navier-Stokes equations, we are going to derive Cauchy equations, okay, which is very important equations when you go for differential form of linear momentum equations. So, basically we are talking about linear momentum equations in differential forms, that is what, and that equations derive is the Cauchy equations, which is we will going to derive it, which is the basic foundations of computational fluid dynamics. Today you can Google the computational fluid dynamics and you can see what are the challenging problems we have been solving in this era. So, that is what the basic things, and let us, as I said it earlier, that we follow the book of Simbala book, which is having a more interesting derivations as well as a series of illustrations, which makes the problem which makes really the problems to understand the fluid mechanics problems. So, that is the strength of this book, and today's there are a lot of MIT open courseware are there, and I just encourage you to look at that MIT courseware. No doubt they have the mathematical components is more, but if you try to understand the physical concept, you look at Simbala book, and intermediates book is Frankman White book, which considers mathematical part as well as a series of illustrations and solved example problems. Let's before going to this, let I give a solution sheet, okay, CFD problems, okay, computational fluid dynamics problems, where here we have used a CFD software is called Flow 3Ds, and we are solving the very basic things as I discussed in my first class is the velocity field, the pressure and the density. That is what we look at. That is what we look at to solve velocity field, the pressure field and the density field. When you have that problems, here we have considered a problems with a bridge pier, okay, and here if you look at how the velocity field changes with the velocity field, which has a component of scalar component and in 3 directions, okay. Here I am looking just Cartesian coordinate systems, okay. In that I have the u v w. So, this is small v, the scalar component in x directions of velocity field, which is a functions of space and the time. That is what we I try to introduce in the very beginning classes, okay, to say that the scalar components having these functions of positions and the time, as it is a Cartesian coordinate systems, we are defining as a x, y, z and the t. It is the same way if you talk about small v, which is the scalar components of in the y directions of velocity components, also a functions of x, y, z, t. So, these are all these functions we are talking about, and using these computational fluid dynamics tools for a complex flow like flow around a bridge pier, we are solving it, and what we are getting it, how the velocity fields are changing, how the pressure fields are changing. I am not going more details, if you can understand it, how the velocity field and the pressure fields are changing it, which is a functions of space and time, we are getting the solutions like that. Now, if I go for the next ones, if you look at how do we get these computational fluid dynamics solutions? By solving these equations. Okay. Solving these equations, which is known as very famous is Navier Stokes equations. No doubt it has the limitations, which we will discuss more details, that what type of limitation is there to solve these fluid flow problems. Okay. But if you talk about this Navier-Stokes equations, which is looks like a nonlinear equation formats in a functions nonlinear partial differential equations, which have a functions of u, v, w, the scalar fields, as well as you have pressures, you have the density. So, that is what is the equations when you solve in a Navier-Stokes equations with certain assumptions, which I am not telling to now. We can solve these real life problems to know it, how these the velocity fields are changing it. Okay. How these velocity fields, you can see these vectors, you can see the vectors, you can see how the grid patterns are there. So, if you look at that, the solution of Navier-Stokes equations gives us to get a approximate solutions of these problems. That is what is possible today. That is what it happened in last 3 decades. The computational fluid dynamics is a major tools for us to solve many real life fluid structures, the environmental problems. Now, today I will talk it how we can derive these Navier-Stokes equations step by step. Having the knowledge is that we have this velocity field, which is a function of the space and the time, the density is a function of space and time. We also hypothesis of continuum hypothesis. That means, we can use these functional behaviors to characterize the flow patterns. Looking that assumptions, if I go for next ones, I will give a today's about the great professors of Cauchy professor, which is way back 1857 and all, which is long back. Okay, it is almost 200 years back. The equations which is derived, this is Cauchy equations what we will talk about today. I also talk about the trace tensors in the fluid flow. Trace tensors in the fluid flow, because in a solid mechanics you know about trace tensors. Okay. But today let us talk about trace tensor in the fluid flow, and we will also talk about for a simplified cases that when you have a infinitely small control volumes. The idea behind it to, as I said it, that I have the functions of u, v, w is a scalar field, functions with a space and time. If I am to derive it and make a small infinitely small control volumes where these functions are continuous, then I can use a basic Taylor equations to solve the problems. That is the very easy concept what we will follow it to consider a infinitely smaller control volume. Okay. So, that we can apply the Taylor series concept to derive these the components of mass flux and momentum flux. The same equations we can look at in terms of Newton's second laws, and we will give a very brief informations about the introductions level on Navier-Stokes equations. Before going to the fluid flow problems, let me sketch very simple things, like I have the flow like this, okay, and I have the upstream flow and is going out like this. This is the boundary, this is a constraint, and as this flow is going like this, just introducing it, how it is different than solid mechanics and the fluid mechanics. So, if you look at the very basics way, that if I consider these points, I will have some sort of velocity distributions like this. Velocity distributions like this. If I consider at these points, definitely I will have a more velocity as compared to this, as the area of the flow has reduced here. So, that way I will have more the velocity, but that is what I can have in the sketching of the velocity. The very beginning I can sketch the velocity distributions, approximate flow velocity distributions, to understand it, how the flow happens. That is what we really discuss in integral approach concept. If I know the velocity distributions, what is my expected velocity distributions, as no slip conditions and this, I can draw this velocity distribution. But in differential forms, what we do it? We look at, I have a small particles, infinitely small particles, okay, and that is what if it is moving it, okay. As infinite small particles are moving it, as the velocity distribution changes it, definitely it deformations happens it, okay. There is deformations of the fluid particles, okay. Maybe linear deformations or shear deformations, because as these particles are going it, okay, as you know it, this is the particles are going it, that is what will not be the same, because there is a contraction, there is a change of the velocity distributions, it will have the deformations here. Again, if it travels it, again it will change the deformations, okay, it will have a different deformations. That is what I am just illustrating with one fluid particles. But if I look at a fluid particles which is starting from here, that is okay, just to have a as I was explaining that concept is that just if you look at the first I told about the velocity distributions, what is anticipated if the flow is coming and going out, you will have a velocity distributions, no slip conditions, and as it goes you can see that there is a change of the velocities. Because of the change of the velocity field, you can see that the fluid particles which are there, that what will go for a different degree of different type of deformations, linear deformations, angular deformations. That is what is going to happen. That is what is going to have the deformations as the fluid particles are traveling from this to that direction. Same way, if I consider another fluid particles which will also go through the deformations at different stage. So, if you now to try to understand it, that if I consider the n number of the fluid particles and if I conceptually track these fluid particles, how the deformations are happening, that is what is giving me a idea that in a fluid flow, when fluid is moving through, is that there is a different type of deformations are happening. Now, the concept is coming that is what we have to conceptually understand it. When you have a flow systems are going on, there are different type of deformations are happening as there is a change of the velocity distribution, change of velocity distributions, change of the pressure distributions, and the change of density distributions. Besides that, when there is a deformations, as you know from the solid mechanics, that whenever you apply the load on a solid, you will have a stress formations. The stress nothing but it is a internal resistance force per unit area. That is what is the stress. The stress is internal resistance force per unit area. That is what we define as a stress sigma. So, that is what we define as the stress, that is a resistance. As you apply the load in a solid structures, you can see there is a stress, internal resistance force per unit area. The same way, when there is a fluid flow is happening, there is a stress is happening at the fluid element level. We are going to talk about the stress component. Okay? The stress component, which in case of the solid mechanics it is easy to measure it, but in case of the fluid mechanics we have to have a conceptual framework to understand it. Whenever there is a flow systems, there is a stress developments are happening. That is responsible for changing the deformations of, as the fluid particles are moving it, you will have a change of the deformations. That is what will reflect in terms of stress components, that is what will reflect in velocity, pressures and the density field. That understandings has to be there in fluid mechanics. Most of the books as represented in terms of a functions which we mix it, that all these functions are interdependent each other. That is not having a clear cut and cause and effect roads, all are interdependent of the velocity field, the pressure field, the density field and the trace field. Now, if you look at the same concept we are talking about the continuum hypothesis, but here we talk about the fluid mechanics, we talk about the how the stress are happening within the fluid particles levels or at the understanding level. Now, as I tell it that we should talk about trace, okay, because as I given a simple examples that we always have a, whenever you have a boundary and the fluid particles are moving it, there is a stress components. Okay. That is what is deformations are happening, there is a stress component on that. So, if you look at many of the mathematically we define the stress as a tensor and we try to define the fluid mechanics in terms of tensors calculations and all, but being a your undergraduate students I am not going to that levels. Let I try to explain it as simple as possible, that we have the trace components. Okay. Now, let me I define it, what are the trace. Okay. In case of, let me look at this figure, look at this figure, same figures I am sketching again with components. Let I have component of x and I have a y and I have a z. This is the Cartesian coordinates, and if I have a surface, okay, if I consider a surface which is a perpendicular to the x axis, is a perpendicular to the x axis, it is a parallel to the y z plane. It is a parallel to the y z plane, but it is a perpendicular to the x directions. So, when it that, if I define the stress will be the sigma s, the first subscript indicates me it acting on a plane which is having a perpendicularity in the x direction. The second shows that the directions of the stress components. Okay. That's any stress tensors we define it as the two subscripts, one showing about the directions, second subscript shows about the directions. The first subscript shows that on which plane it acts it, if it makes a perpendicular, that is which the directions, that is the perpendicular the plane where it is acting it, and that perpendicular for the normal vectors follows the x directions, that is the plane surface indicators are coming it. So, if it is that I have a sigma x x, that is what you can see that x is there, I can write a sigma x x. When I write same things in these directions, it is acting on the same plane. So, it will be sigma x and y, okay, as it is acting on the y directions. If I these directions, I can write sigma x z, I can write sigma x z. The same way, if I take a surface the x, y and z, that is what is, please remember it in terms of subscript notations, that is what is, this will not be have a confusions here, because what is a sigma x s, what is a sigma x y, what is sigma x z. The same way, if I consider a plane surface, okay, in this plane I can write it as here I will put it as the functions. This is y plane, this is z plane. Okay. I am considering a plane surface which is parallel to the x z plane, and if I getting it this component. Okay. Now, I can ask my students, they can tell it what is these components. Okay. So, if I have a this in case of these x planes, we can get it the sigma x s, sigma x y, x z. Now, if I can ask that to my students who are there in this class, that what will be this sigma? Yes, this is the y plane, sigma y y. What will be these things? Y x, this will be sigma y z, exactly same things. If you look it, these components are written like this. So, now if you try to understand this, the stress is nothing else, it is the internal resistance force per unit area. That is what we are defining the trace components. We are defining the trace component, we are defining the internal resistance force what is happening it. That is what this is, a small infinitely small control volumes I have considered it. In that I am defining the stress field. What do you mean by that? I am defining the internal resistance force what is happening it per unit area, because it is easy for me to derive it. That is the reasons we talk about the trace, but indirectly if you try to understand it, for this smaller infinitely smaller control volume where I have a dx, dy and the dz, the dimensions over this surface I am defining it, what are the internal resistance force are there per unit area. That is the reasons I am talking about the stress field. Please remember that. That means, we are talking about the force per unit areas, we are making it as an internal flow resistance force is happening as n number of fluid particles are traveling it, the definitely there will be the resistance part. That is what is showing it here. The resistance per unit area as a stress components, I can for a Cartesian coordinate systems, I can define the stress components. Okay. That means, I can have a trace tensors. Okay. Let me I write it the trace tensors. So, if I write the trace tensors, that is what will come it as sigma is a stress tensors. I can define as a matrix of 3 by 3 matrix for these smaller control volumes as the components of sigma x x, sigma x y, sigma x z. The same way here I can write it y x, I can write it will be the z x. This way the sigma y y and y z. Here will be the z y sigma z z. So, if you look at these stress tensors, is nothing else, again I am repeating it, internal resistance force per unit area, that is the force components. per unit area we are defining, which may have the 9 components. Okay. The sigma xxx, sigma xy, xz, that means it is acting on the plane surface which is perpendicular to x direction, that means yz plane in direction of x, y and z. The same way it is happening it. If I want to try to interpret it in these directions, that means all these internal resistance force acting along the x directions, they have the component of xx, yx and the zx. This is what the acting in the x direction, this is what acting in the y directions, this is what acting on the z direction, this is what acting on a y z plane, okay. And it has the directions normal to that, that is what is happening in this way. So, if you try to look at these equations as a stress tensors, as a internal resistance force per unit component, that means we are nothing doing great mathematics, we are just equating some of the force components at infinitely small control volume, where we can apply the Taylor series, we can apply basic vector calculations, nothing else. Looking that, let me I go for the next one to tell you what we are going back. Okay. That is what, please do not have a fear about these terminologies and the control volumes. Okay. That is what is, when you want to write for a differential equations formats, the control volume have to be infinitely small control volumes, that is what is the idea. So, that is the reasons you can get the velocity field, the pressure field and the density field. Now, if you look at again, I am, as we discussed, we same Reynolds transport theorems, applying the Reynolds transport theorems, having this B value is momentum, the linear momentum equations. Okay. This is the linear momentum equations. Okay. So, mass into velocity, that is what, when you apply it, I will get the same form as I discussed in Reynolds transport theorems. The sum of the force is going to have the rate of change of the momentum flux within the control volume, net outflux of the momentum flux passing through the control surface. This is what the Reynolds transport theorem. This is what the Reynolds transport theorems, as we discuss more details in Reynolds transport concept. Now, what is the basic difference we have now? Because when I consider a smaller control volumes like this, on which there are the trace tensors, already I define it, trace tensors already we have defined it, which is the, again I am repeating it, is a force per unit area. That is what is a force per unit area. That what can we tell it? This is what the surface force component. That is what, if I multiply with a stress with area, I will get it the internal resistance force components, which is acting on the control volumes, infinitely small control volumes, which will give me surface force component. Besides that, I need body force component, which is it, where you just consider the weight of this infinitely small control volume. If it is that, let me I write it, the force what is acting here will have the body force and the surface force. Okay. So, that is the same things as we discuss in Reynolds transport theorems, the integral approach. Only the things what is different here, the body force we are computing as a integrals, volume integrals of rho g d b. B is the volume here. V star is the volume of these control volumes, which is a dx, dy, dz. Okay. So, it is a parallel 5. Okay. So, you can find out the volumes is will be dx, dy, dz. That is what is integrating on this body force part. What is the surface force? Very easy things. That is what the integrations of sigma I j into n into dA is nothing else, as I try to make it that do not have a very afraid it, the same equations we are applying for a infinitely small control volumes, where there is a trace field as we define it, stress into area, that is what is the surface force. Here you are putting a dot product, because we are not assuming this x, y, z plane with a coordinate axis. So, that is you can have a general format. So, we can get it this is the surface force, this is what the gravity force, and g can also sometimes it is better is represent as the vector components. So, some of the force components we are getting it, one is a gravity force, that is what is the body force, and also getting this what is the surface force. So, now if you look it in the next part, what I am just looking it, if you look at these control volumes, before going to next part, again I will tell it, if I take any stress component sigma xx, please remember it, they are also the functions of space and time. So, we can use the Taylor series and continuum hypothesis to consider the trace components also as a functions of space and time. Now, if you look it, I have the control surface, I am just looking this component, how it is coming. For a control volumes, where is a very large control volumes, I can find out this momentum flux and the corrections factor for this. As I have convert these control volumes into a infinitely small control volumes. So, now the control volume, which is not a bigger control volumes, is a infinitely small control volumes, as I have a infinitely small control volumes. Now, if you look it, I have a components in terms of momentum flux components, I am looking it that I have a component rho into u is the mass flux per unit area. That means, if I put the unit of each component is kg per meter cube into meter per second, that is what gives me kg per meter square and second. That means, mass flux kg per second per meter square is coming it rho into the u. Always you always put the dimensions to check component or understand what is meaning of that. That's what the basic fluid mechanics understanding, that you always substitute the unit to understand what is that. When you have a rho into u, that means the density mass per unit volumes into velocity is meter per second, I am getting it mass flux mass per unit time per unit area, that is what is mass flux. If I multiply it rho u into u, that is what will give me kg meter square second into meter meter for seconds, which is gives is kg m by second square y meter squares. Just that is what the momentum flux per unit area, that is what is the unit of force. Kg is a mass into the accelerations per unit area. That is try to understand it, This is also a sum a force components per unit area. I am getting it because of the momentum flux is coming from this rho u component is going in this direction. Try to understand it looking this unit of this part. The rho u is a mass flux kg per second per unit area, that is what is coming from this surface. What is the momentum flux? Because the mass flux is coming in the y directions, that what if you multiplied with rho u and 2 u, that is what you will give it momentum flux per unit area, that is what is kg mass into acceleration per unit, that is the force is coming due to the momentum flux is what is going on or going out. Same way if you can write it, the rho uu, rho uv, rho vu, rho wu, all you can understand it, all are the nothing else is a force per unit area happens it because of momentum flux is going in x direction because of mass flux of this, y direction because of mass flux in the b direction, that is what is representing, or mass flux representing in the y direction. So, try to understand it that when you have infinite small control volumes, your mass flux is coming in the 3 directions. Also it has the momentum flux in the 9th directions, that is the in a 3 dimension. So, if you compute it, it will have a 9 components, that is a equivalent a force per unit area. As remember it, we talk about the stress is a internal resistance per unit area. Same way with a rho u components, we can look it and physically interpret it is nothing else is a momentum flux per unit area as age equivalent force is happening it because of the momentum of the fluid flow is coming into this control volume or going out from this control volume. How much of momentum flux is coming in, going out from this control volume. Now, if you look at that, if I want to look this component, that how if I take a infinite small control volumes, I know it, my rho uu, rho uv, rho uw, like this I have the 9 components as the momentum flux per unit components are there, and if I define this is here the functions behaviors at this point rho uu. Okay. Just I am putting in one dimensional things, okay, taking this 2 surf. So, my rho uu is at this point which is functions of space and time. If I look at a distance d by x by 2 distance and this is my x directions, using the first Taylor series approximations, what I will get it here at this surface will be rho uu plus, because this is a function second, okay, of first derivative into dx by 2, as the distance is ds by 2 and my x directions is a positive in these directions. If I am to compute here, this will be rho uu minus del by del x rho uu dx by 2. So, for this control volume, if I do not look it fully 3 dimensional, just to simplify it a 2 dimensional way, that there will be a, if there is a rho uu as the functions is a continuous functions at the centroid point, the value will be at this point will have a these first 2 components of the Taylor series will explain me what will be the value at this space as well as this space. And if I look at the net, just subtracting this along this the momentum flux per unit area. That is what you are doing it per unit area. No doubt, if you just subtracted it, you will get it rho by dx rho u dx. Okay. So, this will be cancelled out. So, you will have a dx by 2 and this you will have a rho u dx. If you multiply it with the area, you will get it force due to the momentum flux. That is what per unit area is there. If you multiply it with area, that is what is the area will be the, it is acting over the surface of dy and dz. So, if you look at as earlier in the classes, we try to simplify these terms. We try to simplify these terms. Now, we are trying to write these terms in terms of momentum flux as defined by rho u, what will be component here, also what will be component here, what will be component in these directions, because of rho v is a max flux. Similar way, rho w is a max flux. When it is coming it, that momentum flux what is comes in u directions, that is what is represented. The v rho v is a mass flux what is coming into this, which is having a velocity components, what is causing the momentum flux into this control volume, that is what is representing, and similar is going out. So, if you look at the derivations is a very simple, it is not complicating to things, only the things are there, they assuming it all these functions are continuous functions and they can use the Taylor series to approximations of this. That is what they have done it. And you can get net momentum flux per unit area just subtracted for each directions, okay, x directions with a different part. So, more detail you can look it in a book, but this is what basic concept. Now, if you look at another component, just trying to highlight it here, that this component we can, because it is infinitely small, we can approximation to these ones. That means, again I am just writing it rho v, the change of rho u components in dv, that what we can approximate it, because a smaller control volumes, the dv will be dx dy dz, and we can approximate this is rho u. We can approximate it. This is smaller control volumes. The variations within these control volumes are not that significant. So, you can use this come out these functions and you can write the answer. So, basic you will try to understand it, that how the approximations have done in deriving these Cauchy equations. Now, if you look at as I deriving these things, that we can get it the components as I was just deriving for the x directions. So, same way you can directions for the v max flux in the y directions, z directions. The sum of the surface, the momentum flux components, sorry, the momentum flux components, okay, it's this is defining as a outflow and inflow, the same concept. If you can look at this is the same concept. That is what will come it del by del x rho u plus rho u into u plus, same way I am just writing it rho v u rho z W u this is the volume of the control volume. Now, you do it what is d by dx of change of these functions along the x direction. This is the change of functions in the y direction, change of the function in the z direction. That is what we are looking at. The momentum flux, how it is changing in the x direction, that what will be the net force as equivalent force, and this is equivalent force as equivalent force components. We are getting it by just physically try to interpret it, the force components, because of net momentum flux are coming in. Okay, the fluid particles are coming in, going out. That is what it will be coming the momentum flux, also going out the momentum flux, because of fluid particles are coming into this control volumes, also going out of the control volume. That components we are deriving it, they are gradient in x directions, y direction, z directions, showing you the force components which is acting on this because of the momentum flux what is going it per unit volume, that is the reasons dV is there. Now, if you look at the next slides, what we are looking at, that if I apply that same concept for the all these directions. Now, if I look at just look for the stress field. Okay. Again I consider the sigma x x is a stress which is a functions of space and the time, and I can use Taylor series to approximate how the sigma x x variabilities will be there. Same way as I did it for momentum flux, this is nothing else. The same way, if this is the at these centers I have the sigma x x, what will happen it a surface which is a dx by 2 distance, that is what will come at this part, multiplied with the area, that is what will give a force component. Same way, what is the force component on these directions, I can find out on this surface and this surface multiplied this. Same way, you can have a sigma y x component, sigma z x component. That is what we can look it. I told it the sigma x x, sigma y x, sigma z x all are acting in the x directions. Okay. Over these control volumes, all are acting on the x axis directions. We are just looking at the what is the force is happening it because of along these x directions, because of sigma x x, sigma y x, sigma z x, as their values we can approximate it based on the Taylor series, then we can always estimate it that in a x surface directions, this is what will be the gradient, that is like momentum flux. The same way the momentum flux, we are going to get the gradient in 3 directions, will be representing me that what is the surface force is going to act it. That means, the surface force is acting in, I just write it again, will give us sigma x x y sigma y x plus sigma z sigma z x into dx dy dz. That is the components we will get it. So, you can just understand it that how the same concept of the Taylor series, same concept of the functions variabilities as the stress variability, if I consider it, then I can estimate it what is the force is going acting on this surface level of this control volume. As we have computed for the momentum flux and the surface force components and the gravity force components, now it is quite easy for us to write a basic equations. that it comes like this in x momentum directions. The equations comes like this. If I equate the components of I am getting for this the body force, the surface force components. This is the net outflux of the momentum flux, that is what in the x directions I am getting on this per unit volume. This is the net outflux change of the momentum flux within this control volume with respect to time, that is what is showing it this. So, in a partial differential equations format I can get it this all these components just equating the momentum flux, the change of the storage of a momentum flux, and this is the body force and the surface force. So, if you look at as we did it for integral concept using Reynolds transport theorems, the same we have we are looking it in a differential equations format. The derivations is same, it has a certain assumptions as I am trying to explaining you that these are all the functions and the Taylor series with appropriate control volumes. If you consider it, then we will get it this x momentum equations like this. So, if you can understand it, all are the force components, and that is what is we are splitting we are looking the force per unit volumes of all these terms. Now, in the y directions and z directions we can get the equations format like this. Okay. So, this is for y directions, this is for z directions. So, we can have now the three equations from Reynolds transport theorems as we are applying for x directions and y directions, z directions. I can have the three equations representing this momentum flux in this component and this component. This is because of trace field, this because of the body force component, this is because of momentum flux, and this is what because of change of momentum storage within the control volume with respect to time. That is the summations part what we are doing it. Now, if I look at a very basic vector form which can easily interpret it, and I can write it that equations format, okay, because it is easy to remember the vector as compared to these three equations. You have into rho g is a vectors into sigma I j. This is components. You can just have a dot product, you can get it stress. This is a body force component. Again, I am repeating it. This nonlinear terms also you can expand it, just have this rho v v and change of the momentum flux within the control volumes which with respect to time, that is what is given it. This is what Cauchy equations, C A U C H Y equations, which is derived almost 200 years back. I think with this let us conclude. Today we will conclude this.